Hi everyone, welcome back to Dave's Math channel. This is my second video in a series on number theory. Today I'm going to talk about the greatest common divisor, better known as GCD, and the most efficient algorithm we know for computing the GCD of two numbers, called the Euclidean algorithm. Even though it's the most efficient algorithm known today, it was invented over 2,000 years ago by the very famous ancient Greek mathematician Euclid, I'm sure you're not familiar with. So let's begin. So first, let's define the greatest common divisor, otherwise called the GCD, of two integers. So say we start with 24 and 36. How would you find the GCD? Well, the most crude way to do it is you can list out all the divisors of both numbers. And if you do that for 24, you see you get 8 divisors. I'm not going to read them all off. And then for 36, you get 9 divisors, and you just look at the list of divisors and see which one is the largest one that's common to both, and that happens to be 12. Therefore, the GCD of 24 and 36 is 12. Well, that's the most straightforward method because it's just basically what the definition says, greatest common divisor. List them all, find the biggest one. But you wouldn't want to use this method. It's a very, very inefficient method, especially if the numbers are large. So can we do better? Well, yeah, we can do a lot better. A better method, which is probably the one you probably learned in grade school when you were first computing GCDs, is you can compute the prime factorization of both numbers. And one way you can do that is to make factor trees of both numbers. So you start with 24, you get 2 times 2 times 2 times 3. And you know that's unique because of unique factorization. Fundamental theorem of arithmetic says that every positive integer has a unique prime factorization up to ordering of the prime factors. So you can write 24 as 2 cubed times 3. Similarly, when you do the factor tree of 36, you see that it's equal to 2 squared times 3 squared. Then to find the GCD, you just take the smallest exponent of all the common prime divisors, which in this case are 2 and 3, and the smallest exponent of 2 in this case is 2, coming from from 36, and the smallest exponent of 3 is 1, coming from 24. So the result is 2 squared times 3, which is 12. That's another way to get it. And they actually show a third way here. I don't really like this way, but you can just keep picking out prime divisors one at a time until you're left with a pair that's co-prime. But how do you know it's co-prime? I don't think that's a very good method. Maybe it works for small numbers, but anyway, of all these methods they show, I think the one I like best here is the one on the bottom left. But it still turns out that it's not the most efficient algorithm for calculating GCDs, especially if your numbers are really, really large. I mean, factorization is difficult, even for computers. Like, I think the largest number a computer can factor completely right now, in general, is around maybe 150 digits. Factorization's hard, and that's kind of the basis for our modern day crypto systems. They rely on the fact that large numbers are very, very difficult to factor, and the RSA, which is the crypto system that it keeps all your internet information secure. This involves the reason it's secure is because it involves the difficulty of factoring numbers with about 300 digits. They take two prime numbers, each with about 150 digits, multiply them together, and no computer in the world can, with current algorithms or current technology, factor that within the age of the universe. So, so anyway, just a little heads up on that. So this isn't the best algorithm. How can we do better? Well, the best we can do, I already mentioned it, Euclidean algorithm. A pretty amazing algorithm. Very simple, but it's effective and it works. And I'll just show you how it works. So here's how the algorithm works. You got your numbers um, um, A and B that you want to find the GCD. Well, the first thing you do is you divide A by B. I guess you let A be the larger number, B be the smaller. And then when you divide A by B, you're going to get a non-zero quotient plus a remainder. So the key here is the remainder. You don't really have to worry about the quotient, but you calculate the remainder. Let's call that R of dividing A by B. And by definition, the remainder upon division is going to be less than the second number, B, strictly less than B. So then you keep going like this. You keep going recursively. So now you make R your second number. It turns out that the GCD of A and B is the same as the GCD of B and R. You can prove this. I think they do this on the right. So then you just keep going. You find a new remainder. You take the GCD of B and R, you divide B by R, which was necessarily less than B. You get a new quotient, which we call Q1, and a new remainder, which we call R1. And now, by the same token as the first one, we know that R1 is strictly less than R. And all these remainders are positive, by the way. They're all positive and they're all less than the last one we computed. So you keep going like this. Keep going as many times as you need to until you're left with a remainder that is 0. Eventually, you'll get a remainder of 0. That's another thing you can prove. Well, I mean, actually, that's very easy to see. This is a descending chain. Is uh, R is less than R1, is greater than R1, is greater than R2, is greater than R3. These are all integers, finite integers. So you know that within a finite number of steps, as a matter of fact, that within most R steps, you'll get to 0 because they're all less than the previous one, and you can't go down infinitely too many times. So eventually you will get a remainder of 0, and then the last remainder you get, let's call that R sub I think that's what they call it here. That is your GCD. It's just the last remainder. And the proof is on the right. I don't know if I should go through the proof, but um, anyway, it works. I mean, it's pretty easy to see that the GCD of Ri and I plus 1 at each step is equal to GCD of A and B. Because you're, I mean, R has to be a common factor of both A and B. All the common factors stay intact at each step, basically. And so you keep making the numbers smaller until you get down to a remainder that you can't make any smaller anymore. And that turns out to be your GCD. That's the essence of the proof. So very, very nice algorithm. And very, you can use it for as large numbers as you want. You could do it for astronomically sized numbers, hundreds of digits, thousands even if you want. The numbers kind of exponentially decay. So you know that exponential decays very fast. So you can start with huge numbers and still get an answer within a reasonable amount of time, especially for a computer. So it's a very nice algorithm. And I'll just show a couple examples. So these may be out of sequence. I think, no, but okay, so here's the first example. Suppose we want to calculate the GCD of 1180 and 482. These are pretty big numbers, so it's not that trivial. If you were trying to do prime factorization, this would be a lot harder, especially without a computer. But the Euclidean algorithm is very easy. It's very straightforward. You can do this by hand pretty easily. So first you divide 1180 by 482. You get a remainder of 2, or you get a quotient of 2. And remember, we're not really worried about the quotients here. We're mainly worried about the remainder. So the first remainder you get is 216. You make that your new value of B, your new second number, and you make your first number the quotient. So 482 turns out to be 2 times 216. Or no, just that's the last second number. So you make the second number at each step your new first number, and you make the remainder in your last step the new second number. And you don't care about the quotients. That's true. So now you do the same thing with 482 and 216. When you do that, you find that 482 is 2 times 216 plus 50. 50 is your new remainder, so you calculate the GCD of 216 and 50, and then you get 216 is 4 times 50 plus 16. So 16 is now your new remainder. So now you write, you do it with 50 and 16. 50 is 3 times 16 plus 2. And now you do it with 16 and 2. And at this point, it's pretty easy to see that 16 is even, so it's going to be divisible by 2 once you get a remainder of 0. that means your GCD in this case is 2. Pretty straightforward, and not very many steps. Only required 5 steps in this case. So here's another example. And like I said, the quotients don't matter. If you could just calculate remainders easily, which computers can do, I guess if you were doing this by hand, you'd probably have to calculate the quotients, but for computers, remainders are no problem. Um, so let's just do it for two other numbers here, 12, 20, and 516. The key here are the remainders. So if you take the remainder, mod, they call it, 1220 mod 516 is 188. That's your first remainder. 516 mod 188 is 140. Keep going, 188 mod 140 is 48. 140 mod 48 is 44. 48 mod 44 is 4. And 44 mod 4 is 0. 4 divides 44. So we're done. The GCD is 4. So that's how you use the Euclidean algorithm to find the GCD of any two integers. Pretty nice method and a very useful method too. It turns out, I mean, I don't know how many of you guys watched my last video, but my last video I was talking about linear Diophantine equations and two variables, and there's two steps in the method I mentioned for finding solutions. And both involve using the Euclidean algorithm. First, just the regular Euclidean. There's another algorithm called the extended Euclidean algorithm. I'll go over this next time. It's basically the same as the Euclidean algorithm, except you have to keep track of other numbers. You have to keep track of these numbers that give you a linear combination. And in the end, you'll get the numbers U and V I talked about last time. It turns out whenever you have a GCD, there's just a little heads up here. So if you have two numbers A and B and their GCD is D, then it turns out you can write D as AU plus BV for two integers U and V. U and V are not unique, but the extended Euclidean algorithm will give you two values of U and V. And I'll show you how to do that next time. It's a little bit more complicated out. But anyway, that concludes my video for today on the Euclidean algorithm for computing the GCD of two integers. I hope you enjoyed it. Thank you for watching, and long live math, and I'll see you next time.